Okay, so for this next problem, we've been asked to find the position of the center of gravity for this shape for a 10mm thick plate. So this time what we've got is it's constant thickness, and we'll assume it's got constant unit weight or constant density as well. So therefore we can use that second formula. And so the first formula was using had to calculate the mass of each part or the weight of each part because the weights were different thicknesses. But what we'd find is for this one where they're constant thickness, we'd find that the calculating the thickness times the density, those terms are just going to cancel out in a similar way to these cancelling out. And so we don't really need to do all that. What we can do is we just can cancel we can use a formula using the area instead of using the weight of each component. And so to find the centroid of each component, we just use those standard formulae that we'd seen before. Let me see if I can bring those up. Let's have a look. And so it's in my uni. Let me just go back a bit. So that was for curvilinear shapes. That's like pieces of wire. We're not talking about those. We're talking about 2D shapes like this. And so there you've got a list of all the different shapes. You've got a graphical way of finding the centroid, and you've got the position of the centroid as well in terms of an x coordinate and a y coordinate. And just be careful when you're using these that the orientation might change. You know, this might be flipped over, in which case you'd have to flip over the x and y axes as well. So here they're aligned with the right angle. So just be careful with that. So what we can do is, those are easy to find. To get each shape, we can find the centroid just using those standard formulae. Let me go back again. And then we use the equation. This time we'll be using the equation. I'll just write it to the side just now. I'm just thinking. So the sum, don't know what I'm talking about. And so the position of the centroid of the whole shape, so capital X bar, is going to be equal to the sum of the positions of the centroid of each of the shapes times the area of each of the shapes divided by the sum of all of those areas, so the total area of a shape. And similarly, the y position of the overall centroid of the compound shape is just going to be the sum of the y position of the centroids of each shape times their area divided by the total area. Okay, so the first thing we do is have to figure out what shapes we've got and where they are. And so we're going to have a few different shapes like this. Just do it in red. So we've got a quarter circle in red. So we've got a quarter circle like that. We've got a square here. And we've got a triangle. So what next thing I want to do is I just want to show where I'm taking my x and y axis. And so if I look back, let's just have another look at this. So when I'm looking at a quarter circle, for this equation, the x and y axes are just going to the point of the pi, I guess you want to call it, like the right angle here. And so if I put my x and y axes that way, that's going to work out pretty well. So my x is, I'm going to put my y here. Let me just show it. And it'll kind of match up with what is given in the standard equations. So it'll make our life a little bit easier. They're all aligned. We don't have to worry about which direction they're in. Now, then I'm going to try and call 1, 2, 3. Again, we'll use the black center of gravity. Well, maybe we should use red center of gravity just as the center of gravity of each shape. So I'm going to make that a bit smaller. And then, so the pi, just imagining where would that be? I might just have to change the size of this again, actually, just to make this a little bit easier so we can use the squares, basically, is what I'm thinking. So I'll just make it a little bit bigger so that hopefully that works out okay. Not exactly, but it's pretty close. And I'll just mark things on the squares. That'll do it. I'm just trying to get things lining up with the squares so that I can do it more quickly. So let's just put on roughly where the center of gravity is for each shape. So it might be around here somewhere. So just from thinking about the formulae and working out where they should be, or just imagining trying to balance that thing, maybe it's a bit more this way. Just if you imagine trying to balance it. And then we'll just take that one. For a square, it's easy. It's just smack bang in the middle of the square where the diagonals cross. And for a triangle, you look for the right angle. It's the easiest way, and just look for 1/3 of the way along from the right angle on each side. So you're starting basically with the fattest part of the triangle, and you go 1/3 that way. Here's the fattest part, and go 1/3 this way. And so let's just see if we can get another one of those. So it's going to be 1/3. It's 3 long, so it should be exactly there actually. 1/3 of the way. And then I just give those some numbers. So let's call this. This will be 1 for shape 1, 2, let's say 3. Now, what I'm going to do is start putting some numbers on these axes. So we've got dimensions up here. So we know that that square, you have to go 200 along. It's this point here. So this here is going to be 200. We'll just do it in black. So that's going to be, just do it in thick black. That's going to be 200. This is also going to be 200. If you just look at the dimensions in the drawing up there, this is 200. Oops, it's not going to be 200. That's the whole point in doing this. So that's 400 along the bottom there. So that's 400, 200. And then for this top point here, we've got 200 plus 200. So this is going to be 400. And what we'll do is we'll just mark on where the positions of these centroids are. So let's just a sketch. They might end up not being in exactly these positions, but we'll just mark them on just to make it nice and clear. Okay, so I've just put them on roughly, just guessed where I think they might be just now, just so I can draw them. It's going to come down this way. I'm going to have to here. To here. And then I'll just write down what each of those is. So let's have a think about it. So you're always showing the position of a centroid with a letter with a bar on the top. So we'll start with 1. So that is going to be x bar 1. This is going to be y bar 1. Okay, so the centroid of the first simple shape. This one here is going to be, I'll just draw it out because I'm not going to have space, x bar 2 and y bar 2. And then this one here, x bar 3. So the x position of the centroid of this simple shape. And this is going to be y bar 3. Now, when you're drawing on these centroids, just be careful to always think about, look, is this actually the balance point? Sometimes this triangle might be flipped the other way around, in which case you have to start 1/3 from the other side. Do you know what I mean? And so suppose this triangle was like this. Your centroid would be coming 1/3 this way and 1/3 that way to get the balance point. If you did it from the other end, so if you did 1/3 this way and 1/3 that way, you're going to end up with a centroid, what? It's more like a half, a third way about here. You get a centroid here somewhere, and there's no way that this shape will balance at that point. This nose is going to fall down. So just keep your mind practical. Think about, look, does this look right? Have I got it right? Otherwise, go back and rethink whether you've assumed the right starting point for the x and y positions of those centroids. Okay. So now what we'll do is just calculate each of these. So we'll start with x1 is easy. So x1 is just going to be 200 divided by 2 because it's at the center of the square, y1. So let's just start writing these down. I'll keep them, not fast forward it just yet. So let's just write them all down. And I might do it, just so I've got space. I'm thinking I'm going to have to write the x coordinate, the y coordinate of that, and the area of each shape. So I'm going to need a lot of space here. So x1, so the position of the centroid of shape 1 is just equal to, well, the width is 200 divided by 2, which is equal to 100. Okay, so that position is at position 100 on this x-axis. Okay, so x2, we'll do all the x's first. So the x position of shape 2, so x2 is here. Now, I have to try and remember, I think it's 4r over 3 pi to find the distance of that centroid from the right angle. I think it's 4r over 3 pi, but you just go back for now until you learn them. Come back here. Yep, 4r over 3 pi. I'm just going to try and remember that the area is going to be 1/4 pi r squared. It's easy because it's a quarter of a circle. Okay, so go back again. For the square, I wouldn't bother writing down the formula, but for the quadrant I would. 4r over 3 pi. So that's the radius of this circle is 200, so that's the centre, so the radius of the circle is 200. So it's 4 times 200 divided by 3 pi, and I'll calculate what that is in a minute. I'll not waste your time while I'm doing that in a calculator. And then we're going to find the x position. So remember, it's more like a position now. The x position of the centroid of the third shape, so this one here. So what have I got this time? Well, we know that the position of the centroid for a triangle, let's go back to this again. We've got a right triangle here. It's going to be 1/3 of the way along the side. So if that's B, the centroid is going to be 1/3 of the way along. So it's going to end up here, and it's 1/3 of the way up from the right angle. If you've got a right angle triangle, a bit more complicated when it's not a right angle triangle, how to find that. Probably won't put that in an exam or a quiz. You probably find they end up like this. So let's go back again. So therefore, I'm going to calculate that in a minute when I do the fast forward. x3 is equal to, so 1/3 of the length or base or whatever. Oh, have to be careful though. It's 1/3 of the base, but then we're looking for the position of this, so you've also got to add on this 200. Okay, so it's 1/3 of the base of the triangle plus this 200 here, because we're looking for the position of that, not its location within that triangle, the position in the overall shape. So 1/3 B, which is equal to, oh, plus 200, sorry, that's what I was just saying, plus 200. B, the length, the base of that triangle is 200 millimeters, 1/3 of 266.7, I think, so it's going to be 266.7, 4 significant figures until we get to a final answer. Should probably put in units for all of these, and they're in millimeters. Okay, so what I'll do is I'll finish off this, and then I'll do the same thing for Y, and then what I'll do is calculate the area of each of these, so just using standard area formulas that you again would look up on this sheet here. Okay, so I'll do that, and I'll meet you on the other side of the fast forward. So now I've calculated all the positions of the centroids of all the simple shapes, both the x and y coordinates of those centroids, and I've calculated the areas. So now we can just substitute those into the equations. I'll do one thing first. I'm going to use this a few times. So the sum of the areas is just equal to A1 plus A2 plus A3, which is just equal to, so we'll add those up and we'll get that. So it's 42,000 plus 31,420 plus 20,000, which is equal to 9,1420 milliliters squared. So just doing that separately because I'm going to use it a few times. So what I might do is just calculate, just use the formula now. So because it is a plate that has a constant thickness, we can use the equation, the centroid of the position of the overall centroid is equal to the sum of the positions of the centroids times their areas for each shape plus the sum of the areas. So that is equal to, so let me just work through that. Let's see on the other side. So all I'm going to do is multiply each of these by their areas and then add them all up, divide them by the sum of the areas, and we'll get the position of the overall centroid. And then I'll do the same thing for the y coordinates. So added all those up. What you'll have seen it done, I just chucked that into Excel. It's an awful lot quicker to do it in Excel than it is to do it by hand. But I've just done those calculations for each of these. So I've got a column for x bar, y bar, and a. Then I've multiplied x bar times a, and y bar times a, so this one times this one, and then added all those up, added the areas up as well, divided this by that to get each of those, which is just doing the calcs for this section here. Okay, so that was all I was doing there. Okay, so now we've got our answer. So where does that put us? Let's have a look. So 131 and 156, x 131, y 156. So we're ending up somewhere like, oops, somewhere like 131, that's 200, 100, 130. So it's going to be somewhere about here. And then we've got 156. So this would be about, that's 130, 200. So we're going to end up somewhere around 100, that would be 150, somewhere there, about there. And if I imagine sticking my finger there, would it balance? Yeah, I reckon it would. So it looks like we've got the right answer. So just write down what our answer is. Let's just zoom back in. So the position of center of gravity, what did it ask us for? Center of gravity or centroid? Center of gravity. In this case, they're the same thing because the centroid's in the same location because it's a plate of constant thickness. But it asked us for the position of the center of gravity is x bar equals 131 millimeters. Sorry about my writing. And y bar is equal to 156 millimeters. Let me just move this up. I'm just going to write as per axes in sketch above. Okay, so it just saves me writing too much here, saying it's from the bottom left-hand corner of the shape or something. Just say as per the axes in the sketch above. Whoever's having a look at these can then look at my sketch and figure out what I mean. And that's just got our answer. Okay, so this one was just a plate. The main point of this is it's a composite plate, so you find each of your shapes, you go back and look at your formulae for this, where the centroid is for each of those shapes, and then you use the formula, so these two formula up here, you use those to figure out the centroid of the overall shape. That's all there is to it. Next one. Actually, just one more thing before I go. The main thing here also was that we could only use this formula with area in it because all of these different parts of the main shape all had the same thickness. If that wasn't the case, like in the first example where they had different thicknesses, we would have had to calculate the mass or the weight of each of those shapes and use the formula that's got the mass or the weight in it. Sorry, I should have mentioned that. Okay, I promise I'm actually stopping.